All right. So, hello everyone. In the agenda, it says that I was supposed to be joined by my colleague Fabian, but he could not come because of logistics reasons. So, if you came here just to listen to him, you will be disappointed. So, my talk is called LLVM meets code property graphs, and today I want to talk about this thing, like what is code property graphs and its application in the security and software analysis domain. So a few words about me. If you want to find out more, there is a blog. I'm on Twitter, and also you can drop me an email if you have any questions and such. So I work for a company called Shift Left Security, and we are basically building the tools for custom static code analysis. So my responsibility there is to make it work with LLVM, so that we can handle languages like C, C++, and so on, like more of them. So before we start, want to ask you some questions. Can you see a problem with this code? Anyone? Just shout, like. Yeah, double free. Nice. So it was like 4 seconds. Can you see a problem with this code? Use after free. Yeah, that was actually faster. But can you see a problem with this code? So apparently you can, if you have enough time and power, you can probably spend some ages and to analyze it manually to see how it works and so on. But yeah, that's not practical. Therefore, we kind of have to use some tooling and gently ask machines to help us with this task. So I want to show you some demo. So this is the basic example. The first one was double free. Like, how do you find it with the tooling? So first, you need to create, to load this program into memory, and so that you can run some queries to analyze it. Then it's actually very easy. It's an easy example. So to find double free, we just need, from like data flow perspective, we just need to find a flow from one free call to the other one, where the parameter is the same. So we have a source, which is the parameter of the free, and we also have a sink that is also parameter to the function free. So now, if I run, like, show me all the flows from sink to source, then it doesn't work because I forgot one thing, all flows. Here we are. So it says that the first call is at line 6 in file M, and the second one at line 8. So you can run more sophisticated queries with that, but we'll get to it in a moment. So this tool is basically built on this idea of code property graphs, and before that I have to make a step back and talk about the property graphs in general. So I assume that you probably all know what the graph is. If not, so basically you have some set of nodes, and those nodes are connected with just some edges, like by some means. And the property graph, it's basically an extension of a graph, or it's also called multi-graph, where the nodes, they may have several edges connected, like 2 nodes may be connected by several edges. And those edges and nodes as well, they may have a number of properties, basically like key value things. And the CPG, the code property graph, it takes several representations of the program. Namely, it combines AST, it combines the control flow graph, and program dependence graph. So in the end, basically you have this multi-graph somewhere in memory or not. And normally there are tools like Neo4j or Apache something that allow you to work with those graphs. So basically you can just run some queries, like if you do with SQL, you can just like select from blah blah, and this is basically what happens here in this example. So we just run queries against the database. So the beautiful part of this code property graph, or at least this implementation of it, that it's kind of multi-layered thing. So at the on this example, at the very low level, you have just like rough database representation, and it's not really nice to work with as a human being, because you just need to write lots of boilerplates for some things. So for the code property graph, there is another level that adds some more like syntactic sugar so that you can run some simple queries and find more information. There are more overlays, and all of them are they are domain specific. So for example, in our application, there are some specific overlays for web applications saying that, okay, you have basically you just like load the CPG into the program, and then you run a query like show me all SQL injections, and it shows the flows from API route to some place in the code where the SQL injection may happen, and it may be exploited by the user. Yeah, so if you're familiar with LLVM or Clang and its architecture, then you will recognize this slide, basically. So what CPG is, it's just another intermediate representation that just presents the program. So at the front end, there is a number of front ends for each language, so that they emit the CPG, and then CPG is being used by the backend. So currently, originally we were using the Neo4j. It's the graph database, but it's like too general, and it just doesn't really fit our needs, and it was too slow. Because if you want to analyze some big projects, and you should load the whole database in the memory, and for some projects it may require like hundreds or tens of gigabytes. So an OverflowDB is just the same graph database that stores the information. It loads the information lazily, and if it doesn't need anything, it just can overflow it on the disk. So basically, if you don't have enough memory on your machine, you can still use it, but you pay with performance because of the swaps with the disk. So, and what I've shown, this command line tool, it's called Ocular. There is a counterpart, it's called Yorn. So the Yorn is the open source part. It's mainly targeted for C and C++, and it's using the fuzzy C front end. And fuzzy means that it's not real compiler front end. It's just sort of set of regular expressions. It's more complicated than that, but that's not important. The Ocular is more it's a commercial tool. But it's very similar to Yorn, its capabilities, but it has just more overlays for domain-specific things like, some enterprise apps and customers and such. So my goal today is to talk more about the LLVM to CPG. So originally, the project was born because we have some customers and clients, they use fuzzy C to CPG, but it's not quite good for when it comes to C++ or when you want to get some better idea of a program. It has some advantages, like you don't have to compile the code. You can just run it on some source files, and it will just work. But so there were many requests to add better support for C and C++. So this is how LLVM to CPG started. The question that I'm always getting when I talk about this stuff, that why it's LLVM to CPG and not Clang to CPG? Because I mean, it's like obvious that you can get much better information from the source code. And if you go to the LLVM level, you lose some information. So we acknowledge that, but we also were curious about some other parts, like what are the other advantages and disadvantages. And the other one is integration. It's arguable, but in my opinion, it's much easier to get LLVM bitcode than connect some Clang tool to archaic build system, or let's say some Xcode projects on macOS platform. Yeah, the other part that supported languages. So if we want, let's say, it's very common on macOS platform that Objective-C code mixed with Swift. For that, you cannot use just Clang. We would have to combine Swift compiler and Clang compiler and somehow cooperate with this. But because of the LLVM, like as a baseline, we can just use multiple source languages in one place. And also the language feature set. So C, C++, Objective-C combined, they are just huge. We could have built the support for that, but it would probably take several years. And with LLVM, it's much, much smaller. That basically means that the time to market is much faster. Yeah, so these are the conclusions. Some of them, arguable, but that's the current state. Yeah, so the strategy was that we take LLVM bitcode as a baseline, and then basically oriented by feedback, we just basically customers say, okay, we don't see something in Objective-C code, and we just add support for that. And we are driven by feedback in this case. So previously I mentioned that we have AST, right? The part of the CPG is AST, but we kind of don't have that at LLVM level, but still we can mimic it. So on the left, there is a very simple function identity that just takes a parameter and returns it. And on the right, you can see the LLVM bitcode that just not optimized does the same. So first we made kind of assumption that, okay, we'll treat every LLVM instruction as a function call. So it's not really useful especially for the user, for human beings who use the tool, because it just doesn't make sense, like loads and stores, like it's basically working on the assembly level, not as nice. So then we applied some, made some other assumptions, and basically, okay, we specialized some of those instructions, and basically load and store, they are just assignments with indirection, so that we could build in the end from this bitcode, we could build the AST that looks like this. So it's not one-to-one mapping, just as an example. Then with this AST, we could build add CFG connections. Yeah, and with this code, we can, now it's full, now it's complete, and we can run some things, some queries, and find some nice properties. So, yeah, as I mentioned, we acknowledge that we lose the information, but we are still curious, like what kind of information we lose. And the one is comes about types, because this is probably the most interesting part when you do analysis as a security person, because what I observed, people look for things like, okay, find all the members named length, and see if this length can be controlled by something, and if this length is participating in the malloc calls, for example, because then you can probably exploit this stuff. So with the names of the structs itself, of the types, they are there. Most of the time, they are in place and they available. But we definitely lose the names of the members, because for LLVM, it just doesn't matter. It's just like indices, 0, 1, 2, whatever. But we still can look at the debug information, and if it's present, of course, and attach the right names for structs. But that's certainly not the case for unions, because at the source level, we kind of have two members of a union, but at the LLVM level, it's just like one field, like with one property, and it's always so from the call, like to get element pointer, it's index 0. We cannot know whether it was using the A or B in this example. Yeah, the other part that was a bit surprising, not unexpected, but the ABI plays a huge role in this conversion. So at the source code level, we have a function that takes a struct as a parameter and returns a struct. And if on the CPG level, if you want to run a query, okay, find all the functions that return the struct, what's its named, color, then you'll not find anything. Because at the LLVM level, it returns void, and instead it takes two structs as the parameters. Yeah, and it gets even worse with different types, because in this example, these are all doubles, and they are kind of passed as a single thing, as a struct. But if we change that to integers, then because of the of the ABI of this specific platform, you don't even have structs. So there are just like two numbers, and that's it. They are then kind of decoded by the machine. Another part, surprising one, was the constants, and it's actually by far the biggest problem. So if here in the function main, we define locally a constant that holds a number of pointers to some functions, at LLVM level, it will be a global variable. And global variables are not very nice when it comes to the data flow tracking and code analysis, because you can do like intra-procedural analysis, and it's kind of small because you have just one function. But if you need to also analyze the global variables, then you have to find, okay, who may write to this, who may read from this, are there any aliases, and so on. It just, the search space explodes. and that gives us like really hard times to get it right. Yeah, just as a workaround so far, we're kind of whitelisting some edge cases like this and making them, basically putting them back like locally in the function. But it's not a universal solution, unfortunately. Yeah, this is the other part, like the biggest problem. Well, not the biggest, but one of the big problems that I just faced several weeks ago. In source code, you can define a type in a struct, in a header, like struct, and then you include this header into two different compilation units. Then you compile them both differently, and at the LLVM level, you have two bitcode files that have types like struct point and struct point in the other module. If you load them into the same context, then LLVM must rename those to avoid collisions, because basically the types are stored in just like map, basically, like key value storage. And apparently there is no good solution for that. So we want to deduplicate these types, but there is no way to do it, at least currently using LLVM built-in things. So this is one of the examples why it doesn't work, because in LLVM, types are considered equal if they point to the same object, basically. So all the types, they are allocated on the heap, and if you have two different contexts and you ask two floats, they are the same type, right? But LLVM considers them to be different. So the first attempt to solve this problem was to use the function called isLayoutIdentical. You can just run it on a struct and it says yes or no, but it doesn't work. So the structs on the left, they have identical layout, and yeah, it's all correct. But on the right, LLVM does not consider them to be identical, because this function just checks that all the members, they have the same type. But in fact, so in my opinion, it's under-implemented in the base case. That should not be like that, or it should be renamed like is members identical. That would be more valid thing. So we discovered it much longer in the implementation and had to find some other solution. And the solution that we used that also didn't work well, the IR linker, or also there is a command line tool called LLVM link. So basically, it just tries to combine two modules and to eliminate as much types as possible. So in this case, it works perfectly because there is just one type point left and we can use it. But in this case, if you have two different types from the user point of view, like point and tuple, but they have the same layout, one of them will be eliminated, and so basically we're losing even more information. So yeah, I would suggest you don't use IR linker if you want to preserve the type information, or be careful, because what it also does, it may just screw the types in a way that there may appear a type that just was never existed in the high level thing. Of course, you should not rely on this information and so on, but still we want to rely on this. So our attempt to solve the type deduplication problem was inspired by tree automata and ranked alphabets. So basically, a ranked alphabet is just a set of symbols, and each symbol has a number of parameters. You can think of it as like functions, and you can combine those functions to form a trees. And this is where the tree automata comes in, and each tree can be represented as a string, like single string. So then our task to just encode the types into such trees, convert them into the strings, and yeah, then basically we compare the thing. So the next part I wanted to show you, I tried to put it on the slide, but it just doesn't fit. I will try to explain it a little bit. So it comes, yeah, it's about Objective-C. So that was actually very easy to, the easiest part was to recover the information from Objective-C, because it's all there in the bitcode. But there are some quirks, like Yeah, should have found a nice picture for that, but I didn't. Yeah, so I'll try to explain using this example. So in Objective-C, each class has a superclass and a meta class. This is by definition. And a meta class of a class is the meta class itself. And the parent class of a meta class might be either some other meta class or might be the class that defines this object, like in the first place. So it's very mixed. Yeah, just to mention that part. Yeah, I think it went faster than I expected. I probably missed something. Yeah, I'll just say what I missed to say before. So one of the big problems in this case, or of big issues, because the CPG thing, it has kind of two users. One is explicit user, a human being that is sitting and running those queries, and the other user is the data flow tracker. And this is where we just don't have the right, there is no right answer, like what to do, because in LLVM, if you run if you optimize the bitcode and you load it into the CPG, then you get much smaller thing, and data flow tracker is much more happy about that. But as a user, you basically, again, you lose the information and you cannot work with this. So this is, one of the kind of dilemmas that we have. So our next steps for this project are basically to make it stable and to add more languages, like more features from some other languages. I don't know, like Rust, Swift, Fortran. The other part that we are kind of started working on, but not there yet, is we want to hook back into the Clang, into the AST, and just basically extend the bitcode, like the CPG representation that we have based on the bitcode, so that we don't really rely on the debug information, because it's not as nice. It doesn't always work, especially if you have different versions of LLVM and different versions of compilers, and so on. Yeah, and the other part that we want to analyze more projects and to get some results, because the original work on the core property graphs, Fabian, actually, the colleague who could not join, they analyzed the Linux kernel and they found some vulnerabilities that were not known before that. So we want to kind of try to do it with some other projects. So some resources. If you're interested, I do recommend you to check out Yorn. It's free, open source and such. There is also Ocular. It's a commercial product, but yeah, maybe you are interested in it at your company. So I did not talk, type equality. So I wrote down the thing. I think I would be happy to actually contribute it back to LLVM, but I still have feeling that it's a bit too complicated and over-engineered. So I'm kind of trying to get some feedback from LLVM folks, and it's not really successful so far. So if you have some comments, please be my guest. Yeah, the last point, it's the link to the other talk that is more general, like how you build tools based on LLVM. It's, given at Euro LLVM, it's based on my experience building such tools. So I decided not to cover the same parts in this talk and just to refer the other one so that I don't repeat myself. Yeah, so I think you will get a longer break after this talk. So if you have any questions, I would be happy to answer them.
Questions in the front?
Yeah, please.
Do you have any figures of the performance to generate CPG for, I don't know, based on the number of lines of code of some project? Like you said, the Linux kernel. How much time did it take to generate the actual final CPG or something like that?
So the question is, how much time does it take to generate CPG for some projects?
Estimate of the performance of the
So yeah, generally it depends on the front end, but for LLVM to CPG, I can say that for I tried it on Blender, which is quite big, but it wasn't a full project, and it was taking on, I think, on this machine like roughly 15 minutes. And we also did it on the macOS kernel, and that was also like about 15 minutes, just to get this thing. So yeah, it's reasonably fast, I would say. Please.
So, I assume you there know that a malloc is something that allocates memory.
Yeah.
You essentially know what all of the system libraries do. And could you take a project and basically query, does this use any networking? So to verify that some random project you're pulling down from internet is not sending anything on the wire.
Yeah. So as an example, the question is if there are some way to find some patterns right in the code. Can I say it, like this? So or find like
specifically the idea of putting something that you don't know about and saying, does this?
Yeah, what does it do? Like to mining some properties of this program, like does it send network requests? Does it allocate memory and so on? Yeah. So I think it boils down to two things. So I'll get back to this. This thing first. So this is the command line interface. It's like very similar to SQLite, and it's basically the Scala. So first of all, one can write scripts in Scala, interfacing with the CPG, with the database, and having those queries. For example, if you have some domain specific, so this is what our security team does actually. There are projects like kernels and some drivers. They don't necessarily have, they use malloc sometimes, but sometimes they have just some wrappers around those mallocs. So they kind of annotate the functions of interest manually, and then they run some queries. Okay, show me those functions. And that's one part. So it's technically possible. So there is no, if you ask me now to check if there are network requests, there is no such thing, but it's technically possible to build. And this is where the overlays come in. Yeah, as I said, they're domain specific. So we have, in fact, a number of overlays for Go language for web applications specifically, like find all the routes, all the API endpoints in this application. So just as an example.
So if I have a program that, I don't know, say Emacs,
yeah,
I could annotate functions that say this can put something in a buffer, and then this one is affected by X global variable, and go, can find me the functions that can this global variable eventually put something in a buffer or change that?
Yes, yeah. So generally you can do it. It depends on the scale and size, but yeah, generally. So this shown this example from the demo. So this is basically what happens here. So it's very simplified, the most simple example. So our security guys, they are doing some really crazy stuff with it, and I'm just not able to reproduce it. But this is basically what you do. You define one part, you define the other part, and then you find some connections. Yeah. Does it make sense? Yeah. Okay. Thank you. Please.
I have two questions about type retrieval in CPG. The first is, how do you handle things like variadic template renderer expansion packs in C++?
So that's the beauty of LLVM, because we don't really have to take care about that. Because the question is, how do we handle variadic templates and such in our case? So because we work on the LLVM bitcode level, this information kind of encoded into the signature, into the name of the function or method. So in this case, currently what we do only just demangle this name so that users can see something reasonable. But it's we have all this information in the string already, so we can parse it, we can rebuild the whole template thing, but it just, no one asked for that.
I ask because I work on a CPG that has this issue where we want to retrieve more complex information about the parameter extensions. The other question I had is, how do you deal with things like a constant erasure in the LLVM type system? So I might want to ask whether or not a variable has constant at compile time that might be plausibly violated by some memory access at runtime. But LLVM doesn't represent the kind of thing inside of LLVM type. So how do you?
So the question is, how do we handle the constant types in?
Or there are erasure specifically by the LLVM type system.
Yeah. Yeah, so far I think we don't have any special treating for that. If it's, I mean, it's the global variable, right, normally, and there is no great support like by the specific of the CPG because of the space explosion. So, I mean, it can be implemented, we just didn't get there. But so far for, yeah, I think in most of the cases when we are interested in the global variables, these are either function pointers because it helps for the data flow resolutions, or the constant, like string constants, for example, so that a user can see that, okay, these are the strings are used and so on. Yeah. Yeah.
So if I understood correctly, this is a data structure helping with static analysis. Is it possible to compare that with something like the Planck static analyzer, or is it just so completely different that it's incomparable?
So you can compare that, I think, to a certain extent. So this tool is more in its, like in a nutshell, it's more like user-driven. So, and I think the audience of this tool is security teams, like red teams, blue teams, who analyze the code. And we don't really have such checks, the same checks that Planck analyzer has. Because, I mean, because there is Planck analyzer, and it's just, you can already use it. So there are other tools. Yeah, but we can do it. Sorry, there was a question. Back.
Yeah, so on this question of struct types being equal or not, I'm kind of wondering because in the end, if you have two struct types that have the same shape, you can basically always replace one for another. So do you know, or does anybody else in the room know why LLVM works like this? Why doesn't it automatically deduplicate struct types? Is that a conscious decision, design decision at some point, or is it just a maximum of history?
Yeah, so the question is more open to the community. So why does LLVM not deduplicate the types by default? So I don't have an answer. I mean, I don't know. Sorry. Yeah.
Maybe it's an answer for the question which was raised. Maybe because in some cases when your structure is super complicated, it's indecidable, or it's super complicated to have an algorithm which can decide whether two structures are equal from a layout point of view. You've designed a solution which relied on some graph and layouts to recursively check if two structures are the same. But there may be edge cases when you use some unions, some GCC extensions or Planck extension where this thing is not going to work because you're relying on obscure features which are not disable at compile time.
Yeah. Okay. The question is. Yeah, it's not. Yeah, but. I mean, I still can comment on that. There is another approach to that. So first of all, in our case, we don't really use the layout equality to decide, but we kind of use the structural equality. So that if a struct, if you draw the structs as a graph or as a tree, they must have equal shape. So this is our definition of equality. And there is another approach. I think it's called, like, based on Hopcroft's DFA minimization algorithm. I think at least my colleague told that this is what IR linker does, or it looked to him that this is what IR linker does. And there is also some other, I think, scheme project that they do this. They use this algorithm, but it uses different equality thing. So it doesn't. I mean, it doesn't fit our definition of equality. So this is why we did it the other way. So there are two questions. Yeah.
I wonder this type deduplication thing. How does it handle pointers? Does it just treat all pointers the same, or does it take time for the pointer to be typed and compare them?
Yeah. So it doesn't treat pointers as the same. So that's the point. And to avoid recursion. So basically, when we build this tree, we rename. We don't take names into account. We just rename all the structs. We just give them some ID, like numerical ID. So basically, if you see the struct that you already seen, like recursive case, you just emit, okay, this is the same struct, and we don't emit anything further. So it kind of, so it's a graph, and we convert this graph to a tree. So there is no recursion in this case. Yeah, there was.
I think, sorry, just to interrupt. that answers my question, because currently pointers in LLVM still have a pointy type, even though conceptually the idea is to get away from that. Once pointers are opaque, that problem just disappears. It becomes trivial because you no longer have forward references, right? And then you could deduplicate by default because historically pointers have pointy types. It's a problem. Thank you.
Yeah. There is just another comment. There is a write-up by Chris Latner. There was about type system change around LLVM 3, and there are some good points on why the type system the way it is currently. Yeah, there were some questions here and one there, I think. Yeah, please.
Yes, the question is when you get bytecode, it's already optimized. How you get back to source code?
Yeah, so the question is when we get the bytecode, it's optimized, and how we get back to the source code. So it's not necessarily optimized. It's up to the users how to emit this bytecode. It can be like totally unoptimized. And to get back to the source code, we can only by the mean of debug information, because all the instructions with the debug information, they have notion like where they came from. And yeah, we can basically reconstruct some interesting parts. We can just look back at the source code and the AST and see what's in there. Yeah.
One more question.
Yeah, the last question. There was one, I think.
Okay.
Yeah.
So you start out with IR, which is fairly standard SSA form, and then you build an AST from that, and then you build your control flow graph from the stripped down AST. I was wondering why you don't build the control flow graph from the SSA form directly.
Yeah, it's a very good question. So the question is why don't we use the SSA form, right, and kind of invent something else? So we have some debates in the team about this once in a while as well. But so basically historical reasons. So the tool was first built for I think with Java in mind, and this is the format, yeah, the way it is. And we have a number of front ends supporting different languages like C#, Python, Go, and such. And I think by now only LLVM has this SSA form in this pure SSA form. So if we want to use SSA form, we would have to change all the other languages, which is, yeah, quite an effort. Okay.
Thank you very much.
Thank you.